Hi, are you thinking about using a CT scanner for your research but don't know how it works or what's involved? Well, don't worry. In this video, I will show you the process, including how to set the sample and how to set the scan conditions and how to get the results. I'm Aya Takase. So today, I'm going to demonstrate our submicron resolution X-ray CT scanner nano3DX. Let's get started. This is the nano3DX, and this machine can achieve submicron resolution. And you can't see it because it's behind the walls, but this is where the X-ray generator is. X-rays come out from this tiny hole here, and it goes to the sample. This is the sample stage. Then the X-ray image goes to this combination of scintillator and a lens, and that lens magnifies the image, and that goes to an SCMOS detector. Again, that is behind this one. You can't see it, but there is a detector here. The geometry we're using here is called the parallel beam geometry, which is very good to achieve a high resolution. This little pink thing at the top, so it's a foam material and it has a lot of pores inside. We can't see them with our eyes, but if you use this X-ray CT scanner, you can see them in 3D. There is a sleeve here, so this is where this sample base is going to be in, and the foam sample is just sitting on top of this pin with a double-sided tape. So we just set the sample on the stage, and you can see the sample here. It's sitting a little short, but we'll adjust it in a second. And what you're looking at here is the data collection software. So just briefly, you have the sample view from the regular CCD camera here, and this is going to be the X-ray view. So let me start the live image. So we don't see anything because there is no sample. So to bring the sample up, I'm gonna click this spot to bring that spot to the center of the view. And this small square you see here is the field of view. It's about a 0.7 millimeters, and I'm selecting this field of view to achieve about a half a micron spatial resolution. Okay, so now you see the sample pretty much centered here, and you see the 2D projection of the sample here. Now, we're going to rotate the sample 360 degrees. That means I have to do this alignment of the sample at 90 degrees too. Let's go to 90 degrees. And actually, it's pretty well centered. Maybe just a little bit. So let's go back to 0 degree. Okay, so now the sample is centered, so we can go ahead and do a scan. And you have different choices on this side of the screen. You have the sample mount and sample alignment is just what we did. And what we're gonna do for scan is this one, continuous scan. When you set scan conditions, you would choose the voxel size that determines the spatial resolution and the field of view. They're related. Also, you choose how many projections to collect, then how much time to spend. Typically with this machine, the scan time runs anywhere from a few minutes to a couple hours. But there are cases you might want to run 8 hours, 10 hours of scans, and you can do that too. But for today, for the demonstration, I'm gonna run just 3-minute scan. So to do quick scan, I'm gonna change the binning of the pixel, set it to 3, to have a little less than 1 micron, 0.975 micron voxel size resolution. Then for the projection, it's 600. By the way, when you change this to 1, this number automatically changes to the recommended value. So when I say, okay, I'm gonna do 3 binning, 600 projections are recommended. And I'm gonna leave the scan time as 3 minutes and have a file name or sample name and click run. And it will take 3 minutes. Now we have a scan results, so take a look at them. I'm going to click open reconstruction window. So on the left we have the 2D projection. In 2D projection, we have 600 of them. You have everything projected onto 2-dimensional plane, but we have 600 of those. And on the right hand side, we have a reconstructed cross section from this orange line. And this is the part of the 3D reconstructed image. Now, when you do high resolution scan, you have to make sure that the center correction is done. I'm going to just go ahead and click auto center. Now you can click reconstruct. This is no longer a projection on one plane. They're all reconstructed in 3D poly. Once you do a scan, you can do different kinds of quantitative analysis. Let me open Dragonfly, the analysis software. So this is a scan I collected beforehand. It took 45 minutes. That's probably more normal scan time. You can see that the noise level is a lot lower. Now with this image, you can separate the phases. For example, in this case, you can separate the air from the polymer. This is called segmentation. And once you do the segmentation, you have 2 phases, yellow polymer and blue air. And again, you can look at whatever spot you want to look at. Now, at this point, you can measure the size of the pores, or you can analyze the aspect ratio of the pores, or you might be interested in the thickness of the polymer, and that can be analyzed too. So let me focus onto this one and hide the image. Okay, so in this view, the polymer wall thickness is color-coded. The purple means it's pretty thin, probably a few microns, and this green and the yellow indicate that the polymer is getting a little bit thicker when multiple pores are connected. It goes up to about 45, 50 microns. So as you can see in this example, once you have the CT scan, you can pretty much quantify anything you can measure from this image, such as size distribution or volume fraction or wall thickness distribution. So now you watched the entire process, you might have some questions. You can talk to an expert or you can just email us. We're here to help you, and thank you for watching.